It's AP time. I dropped the stream and brought it back up, so it's going to be really easy for me to deal with videos and whatnot as we move things around. Hello, AP2. If you're still here from CP, we just did dimensional analysis, but if you're here from AP2, we are going to be looking a little bit at some of the blowpipe lab that we've been doing recently. And specifically what I like to look at is work energy theorem and how we can go about it in a few different ways in order to use it. Most of what you've done thus far in the blowpipe lab kind of resembles something like this, where you know, you're standing here or something like that. Maybe you've propped the blowpipe up on something, maybe you're holding it, I don't know, but you have this blowpipe, very long blowpipe, pew, shooting that maul out and hitting the ground. And some things we want to remember here as we're doing the blowpipe lab is that if our ground is here, you automatically know the time it takes to hit the ground here. That's a given. If you think back to kinematics last year, you know that, and I guess we'll write it as delta y, although I like to call it h for height. You know the equation v naught t plus 1/2 at squared, where a in this case is the acceleration due to gravity. And because the x and y directions are separate, and we're looking at the y direction here, that's why I said delta y and I said gravity, because acceleration due to gravity is what's going on. You know that you're not starting up or down, you're perfectly horizontal, and you wiped that out. So you could quickly just solve for how long it takes to go up and down by saying t equals 2 delta y over g, and then root that. So you automatically know the time, what's going on here. The issue is, as you start using other projectile motion stuff, you start getting into things like, well, Mr. Botzer, I can measure this distance from where it hit the ground. I can call that delta x. And if I know the time it took to do that, then knowing that the acceleration through the air of the object is constant, we can say simply that the velocity is a displacement divided by time. And we feel pretty good there. And this is the velocity right coming out of the gun, okay? So you could call that an initial velocity and a final velocity, or a final velocity as it's moving through the tube, and the same final velocity, whatever floats your boat. Either way, you have the velocity when it comes out of the tube. Now, this is where things start to get a little bit weird, and a shout out to Will, because he was the first person to ever figure this out before doing the lab, so kudos. What we need to recognize here is that as we are looking at this blowpipe here, you are blowing with a force, and hopefully it's a constant force. Well, we can at least assume that. Assuming you're not being like weird on how you blow the blowpipe, like, you know, you're blowing just and it's constant. So you're applying this constant force, and you're applying it over the length of the pipe, which is a distance. We can call that just delta x. And in doing so, if we think about a force and a distance, where the force is in the same direction as the distance, they're parallel, you've just done work. And this also makes sense if we think about the fact that the marshmallow we're shooting out of the gun is starting from rest, and then it's being moved to some final velocity, which you figured out coming out of the end of the gun. So by doing this, by recognizing that what we have going on here is some amount of work being done, and thinking how work is related to kinetic energy, we can really start pushing forward in this lab. And that's a big thing here, remembering from last year. And one of the only things we will need in AP Physics 2 that you pulled up from last year in your introductory physics course is the fact that work is equal to the change in kinetic energy, okay? Which, if I expand each of these terms, we simply have that F dot, remember this is dot delta x, and that dot represents a cosine term there. We know in this case the angle between these is 0, so this is just going to be fx cosine of 0, which is just fx. That's going to equal the kinetic energy 1/2 m, and then because it is a change, we are actually looking at a final squared minus an initial squared. We know the initial here is 0 in the beginning, so that goes away and we just have 1/2 mv squared. So we feel kind of good about that. If we start looking at this though, remember this delta x, that is the delta x of the pipe, not the delta x that it's traveled. Remember, we've got two delta x's here. We've got a length of the pipe and we've got just a general length that it traveled. So I'll subscript these pipe and then length. If you want, you can call that floor. I don't care, whatever. But it is important to keep these two quantities different. They are both delta x's. They are both distances. Some people like to call this x and this d. Some people say d and x. It doesn't matter. It's a variable. It's whatever you want it to be called, but it needs to be separated somehow. Especially if you're calling this over here delta x, in which case, like, oh, well, be careful about that. In the end, though, because we have this f, and I'll let the delta go away, I'll just say xp, noting that it is the length of this pipe, equals 1/2 the mass of the mollo times the final velocity squared. We can get this final velocity right here, and this is important because right now what you're asked to do in this lab is to figure out, and your goal is to figure out some relationship between the length of the pipe and the length the mollo goes. What is this relationship here? Is it just linear? Is it 1-to-1? Is it squared? Is it you know, some slope out here? Is it a cubic? I don't know. I don't know what this is. You don't know what this is either. We're kind of stuck. And that means that if we do have an equation to describe this, the left side, which is representing the length of the pipe, needs to be matched with some length of the distance traveled on this side of the equation. And right now we don't have that. We've got VF squared, but that's okay because we can bounce that right down there. In doing so, we yield ourselves with 1/2 m, and then we get xl squared over t squared. Okay. What is this? Very helpful. So that becomes a helpful thing right there. I'll leave that algebra to you, but in the end, you can figure out some interesting stuff in terms of what this proportion right here, what should it actually be? Now, the real aspect of this that becomes a little bit more challenging is when I asked you to solve for the force. And I guess before I go to that real quick, I'd just like to talk about this back here, this work equals kinetic energy. A lot of people like to start this lab doing pressure. They like to use pressure right up here, and I'd like to just comment on that real quick because you got to be careful right in here. You can start this lab with a pressure, but you need to be a little careful, and we won't really see how to be careful with that until we get to fluids. The reason why you got to be careful is a lot of people think that whenever you're blowing the pipe, or you're blowing the mollo through the pipe, you're building up a pressure and then you're releasing it in order to get the mollo to go. And that's not true. What you're doing is you're applying the same force, which is caused by a pressure, but the pressure is not increasing. It's constant. And that's because as you shoot the mollo through, the mollo is moving throughout the pipe. So you have this change in volume as you get more and more pipe that's occurring. And what's actually happening is you have a constant pressure. So that's something to be aware of. Whenever we get into fluids, and spoiler alert, if we think about what the units of pressure are, pressure being a force per unit area, like a cross-sectional area. So if we assumed the marshmallow was a sphere, the cross-sectional area of a sphere is a circle. What we're going to have here is something like newtons per meters. Whoa, what is that? That is weird. Newtons per meter squared. So we're going to have these newtons per meter squared in pressure. If we want, in the end, we know work is being done here. we need somehow to get rid of these like per meters squared. We need to get the rest of this term up here. I've got newtons, I need meters, so I need somehow for there to be like a meters cubed up here, which is a volume, and that doesn't make much sense. But actually it does. We do have a volume here. In thermodynamics, and as we'll see when we get there, you can do work through a system with the equation P times delta V, because the pressure and a volume is work, and we see that right here because we're looking for a meters cubed. That's a volume, and you have that. For the pipe, this cross-sectional area of the pipe is a circle, which is pi r squared, and you also have a length of the pipe, which, if I just call this some length L, that's pi times meters cubed. Meters cubed is a volume indeed. So because you can measure this and you can measure that, the radius, which will give you the area, and the length of the pipe itself, which you already have, you can technically get the change in volume at a constant pressure, because this pressure here, once again, is constant. Okay, so that also gives you work. It's just, you're basically, when you do this, are just canceling out the areas, because what you have is for pressure, you have a force per unit area, and then you're saying, okay, and the volume it's going through is the area of the pipe times the length of it. The areas cancel away, and you say, hey, look, the force that I'm applying times the length of the pipe, which is a force and a length of the pipe, ta-da, comes back to the same thing. Okay, so just be aware that if you're going the pressure route, you're doing the same thing. Okay, in terms of what is that force, you'll find it via graphical methods. You want to be a little careful. A group in class has already done this once, and it's a mistake a lot of people fall into. The best way I can describe it is, let's say I have an equation like let's just do a linear equation, like y equals mx plus b, right? And you have some data. So, here's our y-axis, here's our x-axis, and then after some data, we put on the graph, throw in a line of best fit. We say, hey, look, here's the slope, and here's the b-intercept, whatever. Maybe it's 0 in this case, I don't know. But you have the slope. And then what a lot of people do is they say, okay, I'd like to figure out a value for y, because I can solve for it. They will use these other quantities and just get a value for y. And that's not exactly accurate all the time, because what you're doing is you're taking two quantities to find something and then working to find the other thing again. It's very circular. It's like I went from here, I found this, and then with this I found that. It's a chicken or egg scenario. Like, what did you actually do first? What is relating to what? The easier thing to do here is, if you have all of the data points, you feel comfortable that that slope is an actual thing. It represents something. And in the case of our data, I don't know if this equation will be what describes your data, based on what you solved above, but if you are plotting two values against each other, this slope, even though it is just a number, it could be more than just one quantity. This slope isn't just saying the slope of the line or the coefficient of the line. This might be multiple things. If you think back to last year, whenever you did Kepler's law, the equation, the period square equals 4 pi squared, and I don't know if you used a or r, but we'll just say r cubed divided by gm. Technically speaking, if you're just using p squared as proportional to r cubed and you wanted to plot all of that, you'd see that there's a huge coefficient right here. And that coefficient is made up of 4 terms. It's made up of 3 constants, 4 pi squared over g, and it's also made up of the mass of the system, which in most cases is just your sun, because your planet's so very small. But if you were in a different scenario, you could look at the slope, pull these 3 out, and say, here's the mass of your sun, just based off of the slope. And the slope tells you a lot of information. So even though right here it just says m, and it's just a slope, it is probably more than just one thing. And that is a really important thing to recognize. Your slope's more than one thing, and if you can find the number for that slope and you can say what your slope equates to, now you can pull all the constants out of your slope and figure out the one piece that is missing, okay? So whenever you get to this step here, you're gonna have a big equation. That's up to you to kind of like work out and how you wanna do some stuff. Whenever you do your plotting, think about your slopes and how that can be useful there, okay? I'm going to stop the video here, but I'll stick around for another 5 minutes or so if anybody's got questions on anything weird. I guess I'll just put like a stop up there. Okay. Anybody got a question on anything? Want to see something weird? See my background with Qui-Gon Jinn there. Questions regarding the intergalactic? Nobody knows. Okay, well, there's just been this problem that I've been working out the past few days, and I'll just call it the ladder problem. And it came about because I'm building a deck at my house, and when I was building the deck, I was climbing a ladder a lot, and it's a very, very simple problem, I believe. I think you can solve it pretty quickly if you give it a little thought. I want a brown. It's a good deck color. Okay, so I've got a deck here. Let's say it's sitting like that. And my deck, you know, these are the boards going across. Very nice deck. To get up to it right now, because I don't have any stairs, I'm using a ladder. Who would you guess? Okay, so what I have here is I have this ladder, and it's one of those extendable ladders, right? So you can like keep making the rungs go up higher and higher and higher. And right now we have the ladder, if this is the ground right here, we have the ladder just, you know, going from the ground up to the top of the deck. So it's going like this, and it stops there. Okay, and with the ladder going up like this, and you know, the rungs of the ladder. Here's the little ladder feet. Maybe you've done a problem like this before, where if you put a person on the ladder at some point, you will note that they have a mass or a weight, or either acting down. The ladder has some center of mass acting down, and there are a variety of different frictional points which will put you in a static equilibrium, where you're saying that the sum of the torques acting on the ladder are 0 around a pivot, and you're saying that the sum of the forces are acting to 0. So you've got a weight, you've got, you know, center of mass of the ladder, and then hopefully like the ground's pushing you back up, and who knows what the wall's doing, right? Maybe the wall's pushing you up based off of a normal force and some friction. Okay, whatever. Well, my thought was this. What if I had the ladder problem, okay? But this time, instead of just having a person standing on it, what if you had this ladder and it just kept being extended, okay? Like, all the way out, as far as you could go, to infinity, okay? So if this ladder initially had some length to it, L, length of the ladder, my question became, how could you determine how far out you extended the ladder before the ladder tips over. And I think it has to deal with setting the pivot right there. Okay? I have a solution to this. I'll let you figure one out. You can actually figure this out just thinking about it and just like verbally stating one. It's not that difficult. You don't have to work out a ton of the mathematics. Once a certain condition is satisfied, it's game over on your ladder. Okay? And you're definitely tumbling down. And the worst part about tumbling down on a ladder like this is if your deck is very smooth, like mine is right here. Maybe it rained or something like that. As your ladder starts tipping down, your ladder is going to start kicking back and you're going to start sliding out. So that's the ladder problem I thought of a day or so ago. Interesting little thing. See if you can figure out how far can it be extended. In terms of L. I will say L for the length of the ladder, M for the mass of the man, and then big M for like the mass of the ladder or something like that. So cool. Take it easy, everybody. Got any other stuff? I will see you in the morning. Okay. Good night. Bye.